Welcome back, everybody. We're going to take a look at Rolle's theorem and this thing called the mean value theorem in this lesson. Okay, so Rolle's theorem says, suppose you have a function f. Let f be continuous on the closed interval from a to b, differentiable on the open interval from a to b, and suppose that f of a is equal to f of b. Then there is some number x equal to c on the open interval ab such that f prime of c equals 0. Or in other words, f has a critical point somewhere on the open interval ab. Wow, what is that all talking about? Let's go through this, okay? A little more, and put this together and try to get a sense of what Rolle's theorem is saying, okay? First of all, let f be continuous on the closed interval AB. So no breaks, no holes, no asymptotes, right? None of that stuff. Okay. It also needs to be differentiable on the open interval. So what does that mean? Well, it means it's continuous, but we've already established that. But in this case, it's going to mean no sharp corners. Okay, so we have a continuous function that's nice and smooth flowing, as I like to say, no sharp corners, right? And suppose that f of a is equal to f of b. That's the last step. Well, what does that mean? Well, that means f of a and f of b are y values. So we have two y values that are equal at the beginning and ending of the interval, okay? a is the x value at the beginning of our interval, b is the x value at the end of our interval, and we want these two y values to be equal to each other. Okay, so let's take a look at the diagram below. We have, the x and y axis set up here, and I have the x values of a and b labeled, and you can see the two dots are at the same height. Those would be the same y values. We can call that in function notation f of a and f of b. Okay, and I'm just going to draw some function that follows these conditions. So I'm going to draw some function that's continuous and no sharp corners, and it starts and ends at the same y value. Now there's an infinite number of ways to do this. I'm just going to do it like this. Kind of looks like a sine curve or something like that. Okay, but really we could draw it any number of ways. Maybe I'll do a few. Here's one that just kind of goes up and down. Remember, no sharp corners. And maybe a third one that's just even a horizontal line that goes across. Okay, certainly I could go down. Okay, but again, you get the gist, I hope. Okay, so lots of ways to draw these functions, but look, they're all continuous. They have no sharp corners, so they're differentiable, and they start and end at the same y value. Okay, well then what's underlined in red up here, okay, says then there is a number x equals c on the open interval AB. So we're just talking about some x value between a and b. Okay, on the open interval, so we're strictly between a and b, and we're just going to call that x value c, right? We're calling this guy a, we're calling that guy b. Let's call this other x value we're talking about c. All right, and it says such that the derivative at that value of c is 0. Well, what does that mean, right? If f prime of c equals 0, it just means what? Slope of the tangent to the original function f is 0. Right? In other words, we have a horizontal tangent line. Okay? So, if we have a function that's continuous, differentiable, starts and ends at the same y value, then there's guaranteed to be an x value, at least one, if not multiple, such that the slope is 0 somewhere between a and b. Well, look at the first purple function I drew. Okay? Certainly that's true. Okay? This has a slope of 0 right about here and right about there. And those are what we're calling the c values. So here I could label this c sub 1 or c sub 2 for that purple function. Okay, if we were looking at the blue function, the slope is 0 up top here. All right, and looking at that x value, that certainly corresponds to some x value between a and b, and I could label that guy c. All right, so that's the idea here. So, there's always at least one, and intuitively that should make sense. Here, look at the green one. That's a slope of 0 all the way across. Okay, so at every single x value in between, the derivative would be 0. There would be an infinite number of points in between a and b in that situation. And with the pink one, it looks like I have 3. There's a slope of 0 there, there, and there. But intuitively, that should make sense. Look, I mean, if you're going to draw a function that starts and ends at the same y value, you got to have a slope of 0 somewhere in between, right? And that's the gist of Rolle's theorem. Okay, and when it comes to these types of problems, usually what we're asked to do is find this x value that we call C, all right, that's usually what we're solving for, that x value that we call C such that the derivative equals 0. Okay, but again, intuitively, try not to overthink this. Any function that starts and ends at the same y value, okay, and as long as there's no sharp corners, right? If there's a sharp corner, there's no slope of 0 on that that upside down absolute value looking function, but that's not differentiable. That's not differentiable between the x values of a and b. Okay, it's not differentiable everywhere. So that's why that condition is important. Okay, if it's a nice smooth flowing curve with no sharp corners, then to start at one y value and get back to that same y value, it's got to have a slope of 0 somewhere in between. Okay, and so let's take a look at a couple problems here and see how this works, and then this leads into really what I consider a bigger item, and that's the mean value theorem. Okay, but here the instructions are typically going to say something along the lines of determine if Rolle's theorem applies. If so, find the value C on the interval AB such that f prime of C equals 0. So it's saying, look, if you see that letter in the parentheses, that's going to represent an x value. Okay, find the x value that we're calling C such that the derivative at C equals 0. All right, so let's see how this is done. Really no big deal. So here we have f of x equals x squared on the closed interval negative 2, 2. And I'm not going to get too into the details up here where it says why is it continuous on the closed interval but only differentiable on the open interval. That just has to deals with the technicalities of the fact that derivatives are limits, and limits to exist need to have left and right sided limits that are equal. But because we're on a closed interval, we can't really come in to the slope of any of these functions from the one side because we're on a closed interval, and yada yada yada. It's not something we need to worry too much about right now. Okay, so don't get bogged down on that detail. Okay, why continuous on the closed but differentiable on the open? Okay, that's just kind of the way it is for some of the intricacies of the limits that are going on. I don't want you to get bogged down with that, okay? But let's take a look at how these problems work, okay? I think I've rambled on long enough. So here we go. We have a function f of x equals x squared on the closed interval negative 2, 2. All right, so to determine if Rolle's theorem applies, we got to ask ourselves these questions. Is the function continuous on the closed interval? Is it differentiable on the open interval? And do the endpoints have the same y value? In other words, does f of a equal f of b here? Okay, so here's our a, here's our b. We're on the interval negative 2, 2. All right, now f of x is x squared. Now, if you had to, you could graph this out, but you guys just want to know. This is a polynomial. Okay, polynomials are of the form, like f of x equals c sub 1 x to the, whole number power. Okay, where this is just any coefficient out front. It could be 5, it could be 1, it could be 3, whatever. Okay, but it's, made up of series of terms, and x has to have a whole number power. Those are called polynomials. So for example, f of x equals 5x to the 5th minus 3x cubed plus 7x minus 1. That's a polynomial, okay? As long as these are all whole number powers of x, okay, you got a polynomial. X to the 1/2, radical x, things like that, they're not polynomials. Now, why am I talking about this? Well, because I just want you guys to know that, you studied polynomials a lot in pre-calc last year. Polynomials are differentiable and continuous everywhere they're defined. Okay, all of them, all polynomials, as long as it's x raised to whole number powers. Okay, this not a polynomial. Okay, not so much because that's not whole number powers once you start dividing. Okay, so it's just like things that you studied last year, no fractions, nothing like that. X to the 4th minus 3x cubed plus x squared minus x plus 2, things of that nature. Okay, those are polynomials. Just be able to recognize them. And no, polynomials are differentiable and continuous. They don't have any sharp corners. They're smooth flowing, and they don't have any holes or asymptotes, so they're continuous. Okay? And so the point of all that is to say when we see these types of problems now, if we have to determine if Rolle's theorem applies and we have a polynomial, we're good to go. Look, f is continuous. Yes. F is differentiable. Yes. Okay? There are no sharp corners. We're good to go. We could sketch a little graph of it as evidence if we wanted to. There's x squared on the interval negative 2, 2. And do f of a and f of b equal each other? Well, in this case, does f of negative 2 equal f of positive 2? Well, let's plug those numbers in and square them, and we get 4 equals 4. So certainly the y values are equal. Okay, so yes, Rolle's theorem applies. I abbreviate theorem THM. Rolle's theorem applies. All right, and that's kind of the first half. We verified this thing applies. Now we can go on and do the rest, find c such that f prime of c equals 0. Well, what does that mean? It means find the value such that the derivative is 0. Find the value of x that makes the derivative equal 0. So what do? Well, take the derivative. In this case, no big deal. What's the derivative of x squared? 2x. If we want f prime of c, we replace the letter x with the letter c. We set that equal to 0. And we solve for c, and in this case, c is 0, which pretty intuitively we can see that right from the graph. When x is 0, the function has a slope of 0. And that's what we're doing. Look, hey, to go from this y value to that y value continuously, we're not lifting our pen, we're not drawing any sharp corners. Somewhere in between there's going to be a slope of 0, and on this graph it's right at x, or what we call c, equals 0. Okay, so again, c, just a fancy x value that makes the derivative 0. And that's how we notate it, the letter C. Okay, so up next, B. We'll start going much quicker with these. F of x equals x cubed minus x on the closed interval 0, 1. Again, we have a polynomial. So is f continuous on the closed interval? Yes, it is a polynomial. 2 is f differentiable on the open interval. Yes, it is a polynomial. Those are just quotation marks because I'm repeating myself in my writing. And finally, does f of a equal f of b? Let's see, does f of 0 equal f of 1 here? So if I plug 0 into f, it looks like that's going to be 0. And if I plug 1 in, 1 cubed is 1, minus 1 is 0, so yes. Okay, therefore, Rolle's theorem applies. Okay, and now we can go on and solve for c. More or less take the derivative. F prime of x here is going to be what? 3x squared minus 1. Replace x with the letter c. And set her equal to 0. All right, so do a little bit of algebra here. Looks like c squared will end up being 1/3. So c is plus or minus the square root of 1/3. You can leave it like that. You can make it c square root of 1 is 1. If you don't like that, you can make it radical 3/3. Okay, any of those are fine. But be careful. Technically, there's only one of these is going to be in our solution, right? We took the square root, so we write plus or minus the square root of 1/3. But given the interval we're working on, we're going to only accept the positive version here. Okay, that came back somewhere on the original interval. All right, and at that value, the slope is 0. There we go. Okay, let's take a look at a couple absolute value functions. Actually, it's the same absolute value function on 2 different intervals. So part C, we have absolute value of x minus 2 on the interval 1, 3. Let's take a look at that, okay? Now, certainly that's continuous. There's not going to be any holes or jumps or anything like that. But what's the issue? Okay, as I draw this, you can probably see, this is not differentiable at x equals 2. Okay, there's a sharp corner there. Since f is not differentiable at x equals 2, which is on this interval, Rolle's theorem does not apply. And we're done. Okay. In fact, if you look at this, there's, let's see, at 1, what's the y value? I'm kind of curious here. At 1, the y value would be up at, let's see, 1 minus 2 is absolute value negative 1 is 1. At 3, we would also be at 1. So look, yes, the y values are equal. But why does Rolle's theorem not apply? Well, we can see that nowhere there's a slope of 0. And again, it's because this is not differentiable at x equals 2. It has to be differentiable over the entire interval. One little sharp corner like that clearly makes it so that there's never a slope of 0, despite the fact we're going from one y value back to the same y value. Okay, so, well, we can get around the sharp corner, so to speak, by changing the interval, but let's see what effect that has. And now we change the interval to 3 to 5, so there's 2. Here's the v. And now if we're on the interval 3, 5, all right, we're dealing with these points. Now look, is it continuous on that interval? Sure is. Is the function differentiable between 3 and 5? Yes, it absolutely is. But what's the problem? The y values, right? The y values are certainly not equal anymore. If I plug 3 into this, take the absolute value, we get 1. If I plug 5 in, we get back 3. Since f of 3 does not equal f of 5, Rolle's theorem does not apply. Okay? And in general, what do you think? Is Rolle's theorem ever going to apply for an absolute value function? No, it's not. Okay? It's either going to, if the y values are the same, you got to go around the sharp corner to get there. If the y values, you know, if you're trying to avoid the sharp corner, your y values aren't going to be the same. Okay? So it's not going to apply to an absolute value linear function. Let's take a look at this cosine function, and then we'll move into the mean value theorem. So f of x is cosine of x on the interval from pi over 2 to 3 pi over 2. Okay, if you want, take a look at this graph. Should have an idea of what the cosine graph looks like at this stage of the game. Okay, at least its first cycle. From 0 to 2 pi. Here is pi over 2, and here is 3 pi over 2. Okay, so in any event, is the function continuous between pi over 2 and 3 pi over 2? Sure is. Is it differentiable? Absolutely. There's no sharp corners. That's a nice smooth flowing curve. And remember, we use the open intervals for that. And are the y values equal? Is cosine of pi over 2 equal to cosine of 3 pi over 2? Well, let's take a look. Yeah, looks like they both equal 0. Okay, they both equal 0. So Rolle's theorem does apply. And again, we're going to find the value between pi over 2 and 3 pi over 2 where the slope is 0. I think intuitively you see it where it is, right? It's right there at pi. Slope looks to be 0 there. So my guess is that c equals pi, but let's work this out and make sure we can do our trig derivatives here, right? So f prime, what's the derivative of cosine? Negative sine of x. F prime of c then is negative sine of c. And we'll set that equal to 0. Divide by negative 1. Sine of c is still 0. Take the inverse sine of 0. And that's just saying, where does the sine function equal 0? And certainly that's at 0 and pi and 2 pi and so on forever. But in terms of the interval we're working on, there it is, pi, as we anticipated geometrically. Okay, but anyway, that's Rolle's theorem. Continuous differentiable function on a closed interval. The y values are the same at the beginning and end of the interval. There's got to be a slope of 0 somewhere in between. Okay, that's the gist of this. Okay, mean value theorem. Let f be continuous on the closed interval AB and differentiable on the open interval AB. Then there exists a value x equals c on the open interval AB such that f prime of c equals f of b minus f of a over b minus a. All right, so how does this differ a little bit from the last one? Well, really by one condition. Let's take a look. Let f be continuous on the closed interval. That was the same first condition of Rolle's theorem. Let it be differentiable on the open interval. That was the second condition of Rolle's theorem, but that's it, okay? Here we're not interested in the y values necessarily being equal to one another, okay? As long as we have a continuous and differentiable function, okay, there's again going to exist some x value we're going to call c somewhere on our original open interval, somewhere between a and b, okay, such that f prime of c equals f of b minus f of a over b minus a. All right. Now in the diagram below, I just have some arbitrary function that that satisfies these conditions. Okay, it's continuous and differentiable on the interval a to b. What does this formula say? Okay, what is the conclusion of the mean value theorem saying? Okay, well, let's break it apart. On the left, we have f prime of c. What does that represent? That represents the slope of f at x equals c, or the instantaneous rate of change of f at x equals c. Let's call it the slope of f at x equals c. What is the right-hand side of this equation getting at? Ideally, it should look familiar to you. We have f of b minus f of a. Those look like changes in y values. We're subtracting y values over b minus a. Those are x values. Change in y over change in x. That's the slope of the function over the interval from a to b. In other words, that's the average slope of the function f on the interval from a to b. Okay, if I draw this line connecting these points, okay, the slope of this line is the average rate of change. Okay, the slope of that blue line gives the average rate of change of f on the interval AB. So what this theorem is now saying is, look, figure out what the average slope is. Okay, figure out this average slope. There's, again, going to be at least one spot, if not multiple spots, where the actual slope of the function equals the average slope of the function. Look right about here in my diagram, right about there. I would say the slope of the function f is equal to the average slope, has the same slope as that blue line. I'm going to call that C1. And I would say there's another one right about here, the way I've drawn this. Okay? But the gist is this. If you have, whoops, sorry about that. If you have any function that's continuous on an interval, okay, and differentiable, again, no sharp corners, here's the average rate of change going down to the right. There's always a place, at least one if not many, where the slope of the actual function is equal to the average slope of the function over the interval. That's why it's called the mean value theorem, the average slope, okay, the average slope value theorem, if you will, okay. And you can play around, you can draw all sorts of functions if you want, and you can see, oh, there's one that's a pretty crazy looking function, here's the average rate of change, and there's tons of points here where the slope is the same, okay. So that's the gist. And again, usually what we're doing is we're looking for the x values that we're calling c that give us that average rate of change of the function. Okay? And if you think about it, Rolle's theorem is this. Because if the y values are the same, if f of b and f of a are equal, what does that make the average rate of change over the interval? 0. Okay, so Rolle's theorem is kind of just a special condition of the mean value theorem where the average rate of change is 0. But here we go. Let's take a look. Determine if the mean value theorem applies. If so, find the value c on the open interval AB that satisfies the conclusion of the mean value theorem. So once again, we'll start with a polynomial, x to a whole number power on the interval 0, 2. So is f continuous? Yes, it's a polynomial. Is it going to be differentiable? Absolutely. So the mean value theorem applies. Okay, and so the idea now is, what does it mean if it applies? It means that there's some number between 0 and 2. There's some number c between 0 and 2 such that f prime of c equals f of b minus f of a over b minus a. That's basically your formula. And what we're going to do is we're going to work out both sides of this. We're going to take the derivative. We're going to plug in c. And we're going to find the average rate of change of the function on the interval AB. And we're going to set these things equal. Okay, so look, off on the side, I'm going to do, all right, f prime of x, not too bad here, 3x squared. So f prime of c is 3c squared. That goes on this side. Okay, I'm going to do f of b minus f of a. Let's see, f of 2 minus f of 0 over 2 minus 0. That's going to be, let's see, f is x cubed, so 2 cubed is 8. 0 cubed over 2, 8 over 2 is 4. And so the average rate of change is 4. That goes on the right-hand side of the equation. Okay, so basically I'm figuring out what this is. and then I'm subbing it in. I'm figuring out what this thing equals. I did the work. I'm subbing it in. Okay? And now we solve for c, right? So not too bad. C squared is going to be what? 4/3. And so c is going to be plus or minus square root of 4/3, which I could write as plus or minus 2 radical 3. Okay? And again, we're on the interval from 0 to 2, so we're going to take the positive version of that. And there we go. All right? And if you want to verify, you can plug 2 over radical 3 into your calculator, and you'll get a number back between 0 and 2. All right? And there you have it. That's the idea. When x equals 2 over the square root of 3, some irrational number, the slope of that function x cubed is exactly equal to the average rate of change of the function on 0, 2. All right, cosine on 0 pi. Well, again, cosine is a continuous and differentiable function. Here we're on the interval from 0 to pi. Okay, so yes, continuous and differentiable. So again, we're looking for c such that f prime of c equals f of b minus f of a over b minus a. The instantaneous rate of change at c equals the average rate of change of the function, the average slope of the function here. Okay, so let's see, f prime of cosine is negative sine, so f prime of what we're calling c, negative sine of c. All right, average rate of change, f of pi minus f of 0 over pi minus 0. Okay, cosine of pi, well, that's down at negative 1. Cosine of 0, that's up at positive 1, right? Let me better label this for you. That's the x value and y value 0. There we go. Okay, so cosine of pi was down at negative 1, cosine of 0 up at positive 1, and in the denominator we have pi minus 0, which is pi, and so the average rate of change looks a little weird, negative 2 over pi. That's the average rate of change of the cosine function as we go from here to there. Well, it's negative, so I'm buying it. All right, and now what do we do? Once again, we take and set these values equal to each other. F prime of c was negative sine of c, and that's going to equal the average rate of change of negative 2 over pi. Let's see, I'm going to multiply both sides by negative 1. And I can take the inverse sine, and that's about as good as it's going to get without a calculator. Okay, if I want, I can punch that into a calculator, and I would expect to get a number back between 0 and 3.14, so on, okay? But there you go. That's as good as it's going to get. We don't know what the inverse sine of 2 over pi is. That's not a value that we're familiar with. So if this was a non-calculator question, you would just leave it at that, okay? And this whole inverse sine thing, by the way, when you're solving for an angle inside of the trig function, you apply the inverse, which is notated with that little negative 1 exponent. And we're applying the inverse to both sides of the equation here. And what happens is those cancel, leaving us with the letter C. Okay, so just get used to some inverse trig notation. Shouldn't be too big of a deal. All right, but again, the big picture here, we took the derivative, we found the average rate of change, we set them equal, we solved for C. A little easier with polynomials, perhaps, than with trig functions. Let's take a look at absolute value with these, okay? So again, let me sketch this out. We have absolute value of 2x plus 3 on the interval negative 2, 1. Now again, we should be suspicious of sharp corners, okay? If there's a sharp corner, the mean value theorem won't apply. So let's see, if I set this equal to 0, I can figure out where this thing splits up. It looks like it's going to be at negative 3/2. So, well, here's negative 2, here's 1. And negative 3/2 would be somewhere like right there. So the V, the tip of the V is right there. Okay. And there's that. There's that. Again, the Y values don't need to be equal for the mean value theorem. But is this thing differentiable on the entire open interval from negative 2 to 1? No, clearly it's not. Okay, so the mean value theorem will not apply since f is not differentiable on the entire open interval from negative 2 to 1. And we're done. Okay. There's, in fact, nowhere there's going to be a slope of this function that has the slope of that dotted blue line. There's only two slopes. There's this negative slope and that positive slope. Never do we hit a slope like that because it's not differentiable. Okay? Well, let's try to change up the interval. So same function, different interval now. Okay, we're on the interval from 0 to 4 this time. All right. And is it continuous from 0 to 4? Sure as heck is. Is it differentiable on 0 to 4? Yes, it is. Okay, so the mean value theorem will apply here. All right. And again, it says f prime of c equals f of b minus f of a over b minus a. All right. So we got to take the derivative of this function. Now look, here's the thing about absolute value functions. The derivative is the slope, okay? And so really, derivatives of absolute value functions are piecewise. This thing splits up at negative 3 over 2. And we got that by setting the stuff in the bars equal to 0. Clearly, this is where the slope changes. We have some negative slope here. We have some positive slope here. Okay, well, that's the derivative. What's the slope? This is linear. What's the slope of x inside this bracket here? 2. So the positive slope is 2. When x is bigger than negative 3/2, we have a slope of 2. What's it going to be over here? It's negative 2. Okay, so that's how you can find the derivative of absolute value functions. You sketch them out and you look at the slope. Okay, and one side's positive slope, the other side's negative slope. That's all there is to it. Okay, based on where this thing splits up. All right, so look, what does that mean? Well, f prime of c we're interested in, right? What's the derivative of this function? Well, on this particular interval, these are x values greater than negative 3/2. The derivative is just the constant 2. So f prime of c is just 2. There's nowhere to plug the letter c. Okay, it's just the constant 2. But we use that. If we were on a different interval, maybe we'd be using negative 2. All right, so just be careful. Now on the right, we're looking for the average rate of change. So we want f of 4 minus f of 0 over 4 minus 0. So something over 4. If I plug 4 in, we get 2 times 4 is 8, plus 3 is 11. If I plug 0 in for x, we get 3. That's 8 over 4 is 2. And what do you notice? We get back 2 equals 2. There is no place to even plug the letter c. Well, let's think about this. C represents any x value between 0 and 4 where the slope of this thing is 2. And where is the slope of this thing 2? Well, it's a line. So it's always a slope of 2 at all x values between 0 and 4. So what do we say? Well, the mean value theorem applies to every x value on the interval 0, 4. This is a very rare example. Okay, not something you have to worry too much about, that we get like an entire interval of x values back, but talk a little bit about absolute value, so I wanted to show you how this worked out. Okay, typically you're going to be dealing with trig functions and polynomials, and then maybe some product rules and stuff will show up as well that you'll have to get through. Not too much with absolute value. You see a little bit of it with rolls, know that it doesn't apply, okay, but don't get bogged down with it with the mean value theorem. Okay, the big thing with the mean value theorem, if you have a function that's continuous and differentiable, the instantaneous rate of change of c is equal to the average slope of the interval. You figure out what those two things are, set them equal, and solve. Okay? And the easiest example, certainly with the polynomials. But reach out if you have questions on this stuff, and hopefully it sinks in. All right, have a great day.